All right, grid paths problem from the CSES problem set. This is the introductory grid paths problem. There is also another grid paths problem in the dynamic programming category, which is a different problem, of course. So in this video, we're going to look into this problem here. So you can read the task description yourselves. And we can notice that the worst case we can have as an input is having all question marks in the 48 character description array, right? Because if every character is a question mark, then we can move in any other direction, in any possible direction from our current state, right? So the search tree, because we're going to do a DFS, right? So we're going to have essentially a search tree of possible states we can reach. The search tree is as big as it gets if we have only question marks, because we are free in every step to follow any other directions, right? Any other direction, right? Now, there are many observations you can make to prune this search tree. Prune means dropping as soon as we see that the state is a losing state. So identifying a losing state and not continuing our search from that branch of the search tree, essentially, right? So there are many observations you can make. I'm gonna show you like 4 observations, and we're gonna use 3 of them in the development of our solution, which will pass under the time limit. One of them is not needed, but it will optimize our solution time. So let's go ahead and look into these observations you can make. So the first observation is that if you have 3 squares like this, and with black I indicate visited or unavailable squares. With green I indicate the current square, and with red I'm gonna indicate the problematic square. So this state is a losing state. Why is this a losing state? First of all, I'm not gonna go into how you manage to reach this square, and this square. Suppose that you have already visited them or that they are inaccessible, right? So you're checking about this. You're in the green square and you're checking this. Why is this a losing state? Because from the green square you have, let me just zoom in, you have only 3 possible moves. Upwards, right, down, and left, right? These 4 possible moves. If we go upwards and into the red square, that's a losing state. Why is it a losing state? Because we cannot get out of this red square. All the other squares around it are already visited, right? If we choose to go to the right, then the red square is inaccessible. All the squares around it are visited. And the same goes if we go downwards and left, okay? The red square is inaccessible after this one. If the red square is the bottom left square, then that's fine, right? Because we have finished the journey and that's fine. So this state, if you rotate it, let's draw the other 4 cases of this state. Let's just rotate this state 90 degrees to the left every time is what I'm gonna do here. So this one and this one, this is the other version of it, and the last version is this. So green here and red here. So these are the states we need to identify. The first heuristic, essentially, right? Identifying that these states are losing states. So this is the first heuristic. Let me just circle this. And the first heuristic here, which we are not really going to use, okay? Because there are better heuristics. And some of them, most of the time, precede this case here. So let's go to the second heuristic. The second heuristic, which is very similar to the first one, has, again, 3 squares visited. And the current square is this one. And the problematic square is this one. Why is the red square a problematic square? Again, to reach the red square, there is only one option. We're going to reach it from this X marked square, and thus we are trapping ourselves. If the red square is the bottom left square, that's fine again, but otherwise it's not fine. If from the X marked square we choose to go to the right, then the red square becomes inaccessible. So most of the time, this case here will precede these cases here. So essentially for this, the way I draw it, I guess most of the time this case precedes this one here, right? And I say most of the time because okay, if we mark the possible squares that can reach this green square are top, bottom, and right. If we come from the right square, then we might have not reached this state yet. But if we come from the top, if you rotate the case, you will see that we have like reached the condition we have for the second heuristic. If we come from the bottom, then it's obvious that this case is reached before this case. And essentially, for this case, if green is the current square, we just need to check the diagonals, right? So for all the diagonal cells, we need to check that they have more than one free adjacent square to them. Otherwise, we're reaching an invalid state. So this is the second heuristic, which we will use to optimize our solution even more than it's needed. Okay. And the third and most important heuristic, so the third one here, is noticing that if you have two squares like this, the current square is the one in between them, and the other two squares that are adjacent to our current square are not visited, and we should visit them, then this is a losing state. Why is this a losing state? I'm not gonna prove it, but I'm gonna intuitively show you that that because these black squares were visited before the green square, we for sure know that there should be a path between them, right? And if this is a top left, then we know that we visited one of them first, and then we visited the other, right? And because there should be a path between these black squares, then for sure any path you are going to draw between the red squares, because you have to draw a path between the red squares. You're going to visit first one of them and then the other one, right? Because you have to visit both of them once each. If you try to, whatever path you're going to try to draw here, you're going to see that you're going to end up intersecting the path between the black squares, right? And again, if you rotate this condition by 90 degrees, so let's draw it like this. This is the current. No, the black squares are these, and this is the current. So if you rotate the condition again, you will see that because for sure we have a path between these black squares, then any other path we're going to try to draw between the red squares is going to intersect the blue path. And if this is in the edge of our grid, so let's say that we don't have a column on the left side, we know for sure that there was a path from the top left square to the red to this black square. And then if you draw a path from the top left square to one of the black squares, you will see again that this allows us from drawing a path between the two red squares, right? So yeah, that's just for an informal kind of mentioning the third heuristic. You can go ahead and try and prove it yourself why this is a losing state as well. The fourth state we need to check is if we reach the bottom left square. So let's say if these are the edges of our map and we are in this square here, which is the destination essentially, and we have less than 48 steps. So that means we didn't visit each. It means that we didn't visit all the other squares once each. Then this is also a losing state, and we should not continue searching from that state onwards. So the state we are going to use in the implementation is going to be, let me just use pink here. It's going to be this heuristic, and this heuristic. Just by using 3, I think the solution should be passing. Let's go ahead and try and use only 3 and see what we get. So let's just implement the solution. Here I'm going to include the libraries. This library here, which essentially includes everything we need. So we're going to read a string essentially, right? This is a string R. We're reading this in. I'm not going to do the optimization between cin and scanf or whatever it is. You don't need fast output to solve this problem. Anyways, you just read the instructions. Let's call these steps. Okay, just R is fine, I think. Yeah. Description. And what do we have here? Since we're gonna have a searching algorithm, we have a visited array. So this is gonna be 7 by 7, right? And we also have an integer for our answer. So this is initially equal to 0. And let's implement the DFS here. So for the DFS, we need the current row, the current column, and the current step that we are on. So let's define this DFS 0, 0, 0. So we're in the first step, so 0 based indexing for our string, and top left is 0, 0 here, right? And after we execute the search, we're just going to output the answer here. So that's the main function. So let's go to the DFS function now. All right, so let's implement the heuristics one by one. Let's implement the second heuristic first. For the second heuristic, it will be nice to have a function that returns true if the square is active. Otherwise, it returns false, or 1 if it's true and 0 if it's false. So we can define this here. Define active xy, let's call it. And to be active, x needs to be in the ranges of our array, of our grid. The same goes for y. And it should also not be visited. Vx y. There we go. So if that's the case, then it is an active square. Now for the second heuristic, we need essentially to count the neighbors of the diagonal neighbor of our current square. So it will be nice to have a function that counts the adjacent neighbors, right? So define adjacent neighbor count x, y, and this should return active of x minus 1. So the top one plus the active of the bottom one plus the active of the left one plus the active of the right one, right? And then this count should be greater than 1. So if there is only one free neighbor, then that's a losing state. So let's define here a function. Let's call it diagonal check, the diagonal count check. So x, y, and it must be that a and c. Actually, it must be that first of all, xy is active. So if it's not active, then we are passing the check. Or if we are the bottom left square, so x equals to 6 and y equals to 0. So if we are the lower, if this red square is the lower left square, then it's fine, right? And the other case is that a and c should be great. A and c of xy should be greater than 1. So we have more than one adjacent squares active, right? So either of these conditions will make the diagonal cell to be okay. And we can implement this whole check here, the second heuristic, we can call it. For xy, then we just check the diagonals. So we check that DCC of x minus 1, y minus 1, and DCC of x minus 1, y plus 1, and DCC of x plus 1 and y minus 1, and DCC of x plus 1 and y plus 1, right? So if all of them are true, then we have passed the second heuristic. Let's now define the third heuristic. So define third heuristic. xy. So for this one, we just need to check that we have two conditions for this. Either top and bottom are occupied, so node active. Just write this like this. Node active x minus 1 y, and node active x plus 1 y, and active x y minus 1, and active x y plus 1. Right, so this is this first case here. So if that's true, or what else can be true? Let's just write this here. So or then I'm putting a backslash there just to change line here, and sorry, here. And then what else can be true? It can be that the same thing we have here, right? We're just gonna change the false characters here and put them here. So top and bottom are free and need to be visited, so they are active, and the bottom, the left and the right squares are occupied here. So this is this second parenthesis is this second case, and this is, yeah. So if either of these is true, then the third heuristic should trigger, right? And the third, actually, this parenthesis should not be true for the third heuristic to pass. So we just put a no here if it's not true. So here in our DFS now, I think we have implemented everything we need for our heuristics. The fourth heuristic is just a check by itself. So let's check the fourth heuristic first. So, and also collect the answer from it. So if x equals to 6 and y equals to 0, right? So in this case, if steps equal to 48, so we have executed the last step already, then answer is incremented by 1. In any other case, in that case, we just return back because we're either in an invalid state or not. Yes. So now let's implement the third heuristic. I mean, let's use the third heuristic. The third heuristic, what does the third one need? If it's not, yeah, yeah. If the third heuristic, actually, let me just remove the note from here. So yeah, if the third is true, then we return yes. So if this parenthesis we have written is true, then we just return and we prune our search. Second heuristic here, if the second heuristic, like the way we wrote it here, must be true. So all of the diagonals must be passing this diagonal check. So in the third heuristic, in the case that it's not true, then we return. Otherwise, we can implement our DFS normally as we will implement it. V of x and y equals to 1. In the end, we're going to make it unvisited again. So this equals to 0. And then we have up, down, excuse me for this one, left, and right. Okay, so let's implement them one by one. If it's active, if the above one is active, and R of S let's just write this into parentheses, R of S equals to U capital, or R of S equals to question mark, then we can visit that one. So DFS, X minus 1, Y, and one more step. For down we have if active X plus 1, Y, and R of S equals to D capital, or R of S equals to question mark. Then in that case, we can do DFS, X plus 1, Y, S plus 1. And then to go to the left, we can have this one, active X, Y minus 1, to go to the left. And R of this step equals to either left, or R of S equals to a question mark. Then we do DFS, X stays the same, we go to the left, step plus 1, and that's it. And then the right is, it needs to be active. And R of S equals to right, or R of S equals to a question mark. And then DFS, X, Y plus 1, S plus 1. And that's pretty much it. So we have implemented all 4 directions. We unvisit it once we finish with every case. And we are checking for our heuristics and also the final case here. We're counting the paths with this one. Right, so let's test this solution. So first of all, I'm going to compile this. Let me see why. Oh, we didn't write the file. Okay, let's write the file. Okay, right. And then I have the input here. I have typed it from before. So 48 question marks essentially. So let's time our solution. Actually, let's see that it works first. Okay, it works. So let's time. So with all the heuristics, it goes down to 0.178, it seems. So let's try removing some heuristics and see if we can, like, what the result will be. So let's not return here, right? Let's try not returning here. Let's only return if we have seen that it is the final one. If we have finished the path, we count the path and we return, right? But in any other case, we're not going to return. We're gonna continue our search. Let's see how much slower will this be. So now I'm skipping the 4th heuristic, which is identifying that if I'm not in the last step and I visit the bottom left square, I'm gonna keep searching, right? So let's see how slower this is. So as you can see, it's like a bit slower. So 4 seconds slower. Let's try removing the 2nd heuristic as well, which is the one with the diagonals that we have before. So let's just comment these lines out. So write this and then compile and then run. So without the 2nd heuristic, it goes up to 3 seconds. Let's try having the 4th heuristic and the 3rd. So it seems it won't pass only with the 3rd heuristic. Right? Let's just let's test it. Let's submit it like this to see that it fails as well. So solution.cpp. Yeah. So if we submit it this way, with we should get time limit. Yeah, we do get time limit. So let's try now having the fourth heuristic implemented. So we're returning in that case, and the third heuristic. Let's see how good our solution will be. So we're compiling. Did I write this? Let's see. Okay, we're compiling, and then we are timing our solution. So 0.77, it passes. So just with the fourth heuristic and the third heuristic, you can pass the time limit. And the second heuristic will essentially just optimize it even more to reach this kind of times, 0.1. So let me just submit this solution, the best solution, essentially, that uses both heuristics. So essentially, this problem was kinda you had to guess these states and make these observations and prune your search. Like, you're not going to, during a contest time, for example, you're not going to mathematically prove that these pruning techniques you have found or these observations you made are going to be sufficient for your time limit to be dropped. You kind of just have to test this, like, just because it's easy to implement them, right? It's just these easy checks that you make. You check if the cell is active, you check the diagonals, you check the adjacent ones, and that's pretty much it. It's easy to implement them. So you test and see which of them make your search faster or not. For example, the first heuristic that I have shown you here, as I have discussed before, usually this case will supersede a case like this. So it's only going to add, because every time you check for such state, you are wasting time, right? So if it's not going to prune a lot of branches from your search, it's not going to be useful, essentially, right? So you check, you find those checks, you try and check and see which of them work and prune your search tree. That's what you could do in a contest time. If you are not doing this during a contest and you are, for example, trying to prove an algorithm or prove the concept and show the correctness of your solution, then you need to follow a more mathematical way of defining this and proving that these heuristics work. Otherwise, you intuitively see that they work and you just check and utilize them. So let's go ahead and just submit the best version of this code to see what times we get on the remote side. So, okay, let me just, I have just written this. It uses all of the heuristics. So let's go ahead and submit. Okay, so we get accepted, and we can see that for the worst case in the remote side is 0.14 seconds. A little bit slower than the times, no, actually faster than the times I have from my side. So that's pretty much the solution to the problem, guys. If you like the video and the video helps you, subscribe to the channel. And you're highly encouraged to, first of all, try these yourselves. And if you get stuck, it's not bad to check the video and see this. Because, for example, for this problem, because it's kind of guessy. It's not completely guessy, but it's kind of guessy to identify the cases that would lead you into pruning correctly and efficiently your search. It's okay, in my opinion, when you're training to look into this solution. And now you know that actually these heuristics, why is this an introductory problem? Because the heuristics we have seen in many cases can appear in other problems. So by knowing that these heuristics are true, for example, this heuristic here, by knowing that it is true, even if you don't know how to prove it, or if you haven't proved it, or even if you haven't studied a proof of it, you know that it is true, right? And then you can use it in the future for any problem you're going to try and solve, in which it may apply. So anyways, guys, if you like the video, subscribe to the channel, leave a like. It helps the channel grow. And I will see you in the next video.